Next chapter, the rectilinear propagation of light and reflection on plane surfaces. Now, of all the 5 common senses, the sense of sight is perhaps the most important. In fact, we perceive almost 80% of the world around us by our sense of sight. We see the things around us with our eyes. But then, why don't our eyes see these things when it is dark? The answer to this question is light. We are able to see the objects around us because of the light coming from these objects. The light from these objects travels through space and reaches our eyes. When it is dark or during nighttime, as there is no light, we are unable to see these objects clearly. Some objects can generate their own light. For instance, the sun, fluorescent bulb, burning candle can generate their own light. Objects that generate their own light are called luminous objects. Most objects, however, cannot generate their own light. Table, chair, wall, paper are examples. Such objects are called non-luminous objects. If then we see objects because of the light coming from them, how do we see the non-luminous objects? We are able to see them because of reflection of light. These objects reflect light to our eyes. We are able to see the non-luminous objects because they reflect the light of luminous objects falling on their surfaces. So, light from luminous objects fall on the surface of the non-luminous objects, and these objects then reflect this light which travels to our eyes. If you light up a torch in a dark room, you will see tiny dust particles in the air. You are able to see these particles because the light from the torch is getting reflected from their surfaces and travels to your eyes. Next, we talk about rays and beams of light. Now, a source of light produces pulses of energy which spreads out in all directions. The path along which light energy travels is referred to as a ray of light. In diagrams, rays are represented by lines with arrows on them to show the direction of travel. A beam is a stream of light energy which is considered to be a bundle of rays of light. A source of light may produce an infinite number of rays, all spreading out as shown on your screen. The beams that are perfectly parallel to each other are called parallel beams. Those that appear to be converging are called converging beams, while those appearing to originate from a point are called diverging beams. With reference to light penetration, objects are classified as transparent, translucent, or opaque. Transparent objects are those that allow light to pass through them and we can clearly see through them. Examples include ordinary window glasses, still water, clear water bottles, and so on. Translucent objects allow light to pass through them, but we cannot clearly see through them. A good example is the bathroom window panes. Opaque objects like window and colored plastics do not allow any light through them. So now, let's talk about the rectilinear propagation of light. Now, we take 3 equal cardboards A, B, and C with pinholes at the center of each cardboard. A candle is placed at one end as shown on the screen. The cardboards are arranged such that the pinholes and the candle flame are in a straight line. This way, the candle flame can be viewed through the pinhole of cardboard C. When any cardboard is displaced, the path of the light is blocked and the candle flame can no longer be visible at pinhole C. This is a simple demonstration to show that light travels in a straight line. This is called the rectilinear propagation of light. It is for the same reason that shadows are cast behind objects standing in the path of light. A shadow is formed when an opaque object is in the path of light. The nature of the shadow depends on several factors. Let us investigate them. Consider this setup in which there is a light bulb, a cardboard with a pinhole, a pencil, and a screen. We want to shine the light on the pencil, but this light should come through the pinhole. We call such a point source instead of shining all the light from the bulb. When the bulb is lit, a diverging beam comes out of the pinhole and a sharp shadow of the pencil is cast on the screen behind it. If you look at the shadow closely, you will see it has well-defined edges and is uniformly dark. In summary, a point source of light casts the sharp shadow of the opaque object on the screen behind it. The shadow is completely devoid of light. Now let's compare a shadow cast from an extended source of light. We put a ball placed on a stand in front of a screen such that the screen is bigger than the height of the ball. We then light a torch in front of the ball to cast a shadow on the screen behind it. You will see that the shadow cast has a dark zone at the center and a light zone around the dark one. The dark part of the shadow is called the umbra and the lighter part is called the penumbra. If we move the ball closer to the screen, the umbra reduces whereas the penumbra increases. And so in general, the nature of the shadow cast depends on the size of the light source, the distance of the object from the light source, and the size of the object. Shadow formation is also the reason for occurrences of eclipses. Now, an eclipse is a phenomenon of shadow formation in which there is total or partial disappearance of the sun or the moon as seen from the earth. Eclipses are of two types depending on the relative position of the moon, sun, and the earth: solar and lunar eclipses. The solar eclipse or eclipse of the sun occurs when the moon passes between the sun and the earth. When this happens, the moon intercepts light from the sun, thereby casting a shadow on the earth and causing darkness during the day. During a total solar eclipse, the moon moves between the earth and the sun. When this happens, the disk of the moon appears to perfectly cover the disk of the sun, even though the sun is much, much larger than the moon. The sun is 400 times bigger than the moon, but by sheer coincidence, the moon is 390 times closer to the earth. Size and distance cancel out. So the sun and the moon appear to be almost exactly the same size. Every time the moon orbits the earth once every month, it has to pass between the earth and the sun during new moon. And every time it passes, the new moon has a chance to block out the sun. But it doesn't always, and we will see why. However, when it does, a shadow of the moon will make a narrow path across the earth, and those in the shadow will see a total solar eclipse. Solar eclipses occur several times a year, but most often they are partial eclipses where the moon doesn't quite line up with the sun. And when the moon and the sun are perfectly lined, the moon is usually far from the earth in its orbit to completely cover the sun, creating an annular eclipse. During an annular eclipse, the sky remains bright. Even in the rare cases of total solar eclipse, the moon's shadow is most likely to fall in the 70% of the earth, covered by water, and very few people, if any, will see it. The total eclipse, which never lasts more than 8 minutes, allows us to see the sun's atmosphere, which is normally not visible because of the brightness of the sun's disk itself. Red prominences in the rim of the sun's disk, called the corona, which now surrounds the circumference of the moon, can be seen at the same time as the scars in the sky. A lunar eclipse happens when the Earth blocks some or all of the sun's direct light from reaching the moon. This takes place only during the full moon, which happens every month. When the Earth blocks the sun's light, it can cast two kinds of shadows on the moon: a larger penumbra and a smaller, darker umbra. A total lunar eclipse happens when the sun, the Earth and the moon are in total alignment and the moon falls within the Earth's umbra. Total lunar eclipses turn the moon into a dull red body. A partial lunar eclipse occurs when the Earth, moon and the sun don't perfectly align, so only a part of the moon passes into the Earth's umbra. The Earth's shadow appears very dark on the side of the moon facing the Earth. A penumbral lunar eclipse occurs when the moon passes through the Earth's penumbra. The event is so subtle that most people don't even notice. The moon will appear just slightly darker than usual. Lunar eclipses occur up to 3 times a year and can last up to 1.5 hours because the moon is much smaller than the Earth and takes time to pass through the Earth's shadow. So the solar eclipse occurs only during new moon and the lunar eclipse occurs only during full moon. Both new and full moons occur every month when the moon orbits around the Earth. So why don't we have a solar and lunar eclipse every month? The moon's orbit is tilted a few degrees relative to the Earth. So the Earth, moon and the sun don't always align. That's why. Next, we talk about the pinhole camera. A pinhole camera consists of a box with a small hole in a metal or cardboard plate on one end and a screen of tracing paper or frosted glass at the other end. If the camera is facing towards a tree, an inverted, diminished image of the tree is formed on the screen. Light rays from the top of the tree A travel in a straight line and fall at X on the screen. Rays from the bottom of the tree at B fall at Y. So XY is the inverted, diminished image of the tree. If the hole is larger, the image obtained will be blurred. If the screen is replaced by a photographic film, a photograph of the tree can be taken. Increasing the number of holes increases the number of images. The ratio of the size of the image to the size of the object is called magnification. We can also write it as the ratio of the height of the image to the height of the object. It can also be shown mathematically that magnification is equal to the image distance from the pinhole over the object distance from the pinhole. This in effect means that the image height over the object height is equal to the image distance from the pinhole over the object distance from the pinhole. Because it is a ratio of two similar units, magnification is unitless. Let's take an example. A pole 6 meters high stands in front of a pinhole camera 24 meters away. The camera screen is 8 centimeters from the pinhole. Calculate the magnification and hence the height of the image. So, magnification is equal to image distance over the object distance. That is equal to 8 centimeters over 24 meters. We convert 24 meters into centimeters, and that gives us 2,400. Dividing that, we get a magnification of 0.003. This magnification is also equal to image height over 6 meters or 600 centimeters. To get height, we multiply 0.003 times 600, and that gives us 1.8 centimeters. Next, we look at the reflection of light. Now, when light falls on a surface, it is either reflected, absorbed, or refracted. In this chapter, we are interested in reflection. This is the bouncing off of light from a surface. The amount of light that is reflected from a surface depends on the nature of the surface, whether it is smooth or rough. There are two types of reflection of light: regular and irregular or diffused reflection. Depending on the type of reflection, we are able or unable to see images on the surfaces. When a beam of light falls on a smooth surface, the rays are reflected back at the same angles and remain parallel after reflection. This is called a regular reflection. It takes place when light falls on smooth, shiny, or polished surfaces. On the other hand, the surface of a wall or wood is not smooth. When a parallel beam of light falls on such a surface, the reflected rays do not remain parallel. This is called irregular or diffused reflection. A wall cannot reflect an image because the reflected rays travel in many directions. Reflection on plane mirrors. A mirror is a smooth reflecting surface which forms images by regular reflection. Mirrors can be plane or curved, but here we will talk about plane mirrors. These mirrors are constructed by coating silver on one side so that the other side can reflect smoothly. Let's look at the general terms relating to reflection. An incident ray is a ray of light traveling from a source to the mirror or the reflecting surface. A reflected ray is a ray of light that bounces off the mirror surface. The point of incidence is the point where the incident ray hits the mirror surface. It is also the point where the reflected ray leaves the mirror surface. A normal is an imaginary line drawn at the point of incidence and is perpendicular to the mirror. The angle of incidence is the angle between the incident ray and the normal and is denoted by I. The angle of reflection is the angle between the reflected ray and the normal and is denoted by R. Now we look at laws of reflection. We fix a white piece of paper on a drawing board. Draw a line M prime on it and mark a point O at the center of the line. Draw a normal ON to M prime. Next, draw IO, the incident ray, in such a way that the angle IOM is less than 90 degrees. Place a plane mirror vertically on M prime. Then fix two pins, P and Q, on the incident ray IO. P prime and Q prime, the images of P and Q, are observed on the other side of the normal. fix two pins P1 and Q1 such that they are collinear with P' and Q'. Remove the pins and draw a line QR passing through P1 and Q1 to represent the reflected ray. If you measure the angle of incidence I and the angle of reflection R, you will find that they are equal. P, Q, P1, Q1, N and O all lie on the same plane. And so in general, the experiment shows that the angle of incidence is equal to the angle of reflection. In the incident ray, the reflected ray and the normal all lie on the same plane. We encounter this phenomenon of reflection every day. When we stand in front of a mirror, we see our image due to multiple reflections. Light rays from any source are first incident on our body. They bounce off our body and fall on the surface of the mirror and again get reflected from there. This reflected light reaches our eyes and we see our image. Plane mirrors are also used for decorations and architecture. Next, image formation in plane mirrors. Now, consider an object of the letter P. From a point X on the object, consider a ray of light incident on the mirror at point A. According to the laws of reflection, the angle of incidence is always equal to the angle of reflection. From the same point X on the object, another light ray is incident on the mirror at point B, and the reflected ray travels to the eye. The two reflected rays from A and B are divergent. When extended beyond the mirror, these rays meet at X'. Therefore, the image of point X on the object is formed at X'. Consider one more point Y on the object. A light ray from Y is incident on the mirror at C, and the reflected ray travels to the eye. Similarly, another ray from Y on the object incident at D, and the reflected ray reaches the eye. Extending the two rays again, they meet at Y', which is the image of point Y on the object. Equally, rays from all points on the object are incident on the mirror. All are divergent, and when extended beyond the mirror, they form the image of the object. You will notice that the image formed is rect, laterally inverted, of the same size as the object, and its distance from the mirror is equal to the distance of the object from the mirror. Next, rotation of mirrors through an angle. Now, consider this kid reflecting the sun's rays to a friend standing on the balcony of a building. He also wants to reflect the same rays to another friend standing some distance away on the road. If the lines joining the kid to the two friends make an angle of 120 degrees, by what angle should the kid rotate the mirror? To solve this problem, let us see what happens to the reflected ray when the mirror is rotated through an angle. Consider a ray of light IO incident on a plane mirror M1, M2 such that OR is the reflected ray and ON is the normal. Based on the laws of reflection, angle RON is equal to angle ION, which is the angle of incidence. Therefore, IOR is twice the angle of incidence I. Let the mirror be rotated through an angle theta about O, so that M1, M2 primes is the new position of the mirror and ON prime is the new position of the normal. The position of the incident ray remains the same, but the new angle of incidence is ION prime. Angle ION prime is equal to I plus theta. Let OR prime be the reflected ray such that angle N prime OR prime is the new angle of reflection. From the figure, you can see that angle IOR prime is equal to angle ION prime plus angle N prime OR prime. Substituting ION prime and N prime OR in terms of I and theta, we get angle IOR prime is equal to 2I plus 2 theta. Subtracting equation 1 from equation 2, we shall get angle IOR prime minus angle IOR is equal to 2I plus 2 theta minus 2I. And therefore angle ROR prime is equal to 2 theta. And therefore, for a given incident ray, if the plane mirror is rotated to a certain angle, then the reflected ray rotates through twice that angle. So for our case, if the kid has to direct the reflected beam to the other friend 120 degrees apart, he has to rotate the mirror through an angle equal to half of 120, which is 60 degrees. Now, let us talk about one more characteristic of images formed on plane mirrors. These kind of images are called virtual. The opposite of virtual is real. Consider this arrangement simplified like this. When standing in front of the mirror, it seems the image is formed somewhere behind the mirror. But then, there's nothing behind the mirror. For us, the light rays appear to come from a location present behind the mirror. When the rays are incident on the mirror, they are reflected according to the laws of reflection. When extended backwards, they give us the position of the image behind the mirror. Although it appears all the light rays are diverging from this point, in reality, there are no light rays behind the mirror. We say the image formed here is virtual. In other words, it is not a real image. A virtual image is one that appears to be formed in a position somewhere behind the mirror, but in reality, there is no image there. A virtual image is formed when light rays diverge after reflection from the mirror. All plane mirrors form virtual images. Real images are formed by spherical concave mirrors that we shall see in Form 2. And this is because the rays converge at a point after reflection. These rays are real and the image formed is also real. Next, parallax. Now, stick your thumb upright as shown on your screen with a board, a TV or a phone about 4 meters in front of you. The thumb should be positioned right in front of your eyes. Try and position it in the middle as much as possible with your eyes open. Now close your left eye. The thumb moves to the left of the screen. Open both eyes and everything is back to normal. When you close your right eye, the thumb moves to the right of the screen. This apparent relative motion of two objects, that is the screen and the thumb, due to the movement of the observer, is called parallax. When reading measurements from a scale, we are always reminded to avoid the parallax error. To avoid that, we need to know exactly where to place our eyes. we read measurements at eye level. This is a liquid thermometer. When reading the measurement, some people look from above, some people look from below. These are wrong ways of reading scales. We read at this eye level. When you look at eye level, the scale and the liquid column are at the same level. This is the correct value, 70 degrees. But if you look from above, the line of vision looks like this. The object and the scale are at an angle, and therefore the end of the object appears to be aligned to 68 degrees. This is parallax error. Similarly, if you look from the bottom and draw a line of vision, the object and the scale are at an angle. The object appears to be aligned to 74 degrees Celsius. This too is a parallax error. And so, does looking from below always result in getting figures bigger than the actual reading? Not necessarily. In this setup, the object being measured is between the eye and the scale. But what happens when the scale is between the object and the eye? Looking from below and drawing the line of vision, this gives a reading of 66 degrees, which is a lower value than the actual one. So, whether parallax error results in higher or lower readings depends on the position of the eye, the scale, and the object. Now, images formed by mirrors at an angle. Have you ever wondered how images are formed in a kaleidoscope? A kaleidoscope uses 3 mirrors placed at an angle to produce multiple images. When mirrors are placed at an angle, the reflected ray from the first mirror is incident to the second mirror. The second mirror in turn reflects it back to mirror 3. And therefore, multiple images of the object are formed. The number of images seen in such an arrangement can be calculated using the formula n is equal to 360 over theta minus 1. And so if the angle between the mirrors is 90 degrees, then the number of images formed is 3. Let's look at ray diagrams from mirrors at an angle. We start with image formation when an object is placed between 2 mirrors inclined at 120 degrees. So we have 2 mirrors MM and MM1 inclined at an angle of 120 degrees. An object O is placed in between the 2 mirrors. Let OA and OB be 2 rays incident on the mirror MM. OA being normal or perpendicular to the mirror retraces its path, while OB gets reflected along BC according to the laws of reflection. Extending OA and BC backwards, an image is formed at O1. Let OE and OD be incident on the mirror MM'. OD being perpendicular to the mirror retraces its path, while OE is reflected along EF. Extending OD and EF backwards, another image is formed at O2. So when the inclination angle is 120 degrees, we get 2 images, and from our calculation, 360 over 120 minus 1 is equal to 2. Next, image formation when an object is placed between 2 perpendicular mirrors. Place an object O between 2 perpendicular mirrors. OA and OB are the 2 rays incident on mirror MM. OA being normal or perpendicular to the mirror retraces its path, while OB is reflected along BC. Extending the two rays OA and BC backwards, the first image is formed at O1. OD and OE represent the rays incident to mirror M' OD being normal retraces its path, while OE is reflected along OF. Extending OD and OF backwards, the second image is formed at O2. The reflected ray BC gets reflected internally by the mirror M' along CG. The ray CG appears to come from O3, which is the image of O1. Similarly, the reflected ray EF gets reflected internally by the mirror MM along FH. The ray appears to come from O4, the image of O2. O3 and O4 coincide, and therefore we obtain three images, and from our formula, 360 over 90 minus 1 is equal to 3. Try and draw a ray diagram to show the images formed when two mirrors are placed parallel to each other. Finally, we talk about the applications of plane mirrors. Mirrors can be placed at an angle to change the direction of light received by the eye. For example, two mirrors placed at specific angles are used to make optical instruments such as periscopes. A periscope is used in land and sea warfare, submarine, navigation and elsewhere to enable the observer view their surroundings while remaining undercover, behind corners or submerged. A reflecting periscope consists of two mirrors to change the direction of light coming from the scene to be observed. The first mirror reflects light down through a vertical tube. At the bottom of the tube, another mirror is placed at an angle to reflect the light towards the observer.